We've spent the last few videos talking about exponentials, so now it's time to talk a bit about logarithms. It turns out that exponentials and logarithms are inverses, and the inverse relationship is something we learned about in Unit 1, so we'll try to bring that out a bit more as we dive into logs today. But let's begin by talking about the way to convert between these two forms. So let's talk about converting between the exponential form that we have a little bit of practice with, and this new form, which will be logarithmic. So I'm going to start by writing something in exponential form, and then we'll just talk about how it can immediately be turned to a logarithmic form. So let's see, let's take a statement that we know to be true. I'll begin with just an actual statement. So let's take something like 2 to the power of 3. And you all would agree 2 cubed would be 8, right? So I just wrote down a true statement. And then what I'm going to do is give you the equivalent logarithmic form. So this current statement that I wrote is exponential in nature, right? We have the 3 as the exponent on the 2. And then the equivalent logarithmic form would state that log base 2, so logarithms have bases, which we typically subscript. So if you're writing on like lined paper, that 2 would fall below the line a bit. So log base 2 of 8 is equal to 3. That would be the equivalent statement in logarithmic form. I'm going to draw some arrows in there just to build that connection a little bit more clear. So basically the base of the exponential becomes the base of the logarithm. And an easy visual way, for those of you who are like me visual, is I'm just crisscrossing the other pieces of the form. So we'll do a couple more examples. I'm going to back out and generalize it first, but that's the most important entry point to logarithms, just to be able to relate them to the exponentials that we've been studying. So again, the log and the 8 and the 3 would all be on the same line, and that 2, the base of the log, is a little bit subscripted. So I know sometimes it can be a little hard to tell that just because maybe I'm not writing straight or something like that, but everything's on the same line except for the base. So that was a specific example. Let's just generalize that a little bit. I'm going to actually start this time by writing the log form first. So let's say that in general, log base b of x is equal to y. I'm just going to make a general statement like that. And that's directly equivalent to b to the power of y is equal to x. And I'll draw in my little arrows again because I'm sure it helps somebody besides just me. But I just drop the base and then crisscross. Cool. So these are equivalent. The top form again is what we'll call our log form. So if it says change it to exponential form, we understand that's the form on the bottom there. Cool. So the cool thing about studying logs, sometimes people are like, ooh, logs are hard, but if you understand exponentials, you really can understand logarithms because logarithms are just exponents. You can easily convert them. So let's do a couple more together, just writing back and forth in the two different forms, make sure we feel good. And then probably the last thing I'll do in this video is talk a little bit about evaluating logs without calculators. So if I were you, I would definitely recommend jotting down this summary here, because as long as this relationship here is clear, you can pretty much tackle anything that I'm about to talk about. All right, so first example, this will be similar to what you might be asked to do in homework or exit slips. Let's just write 5 to the power of 3 equals 125. That's a true exponential statement. And let's just write it as a logarithm. All right. So again, if you're like me, the little crisscross helps. So feel free to take it if you like. But when I convert an exponential to a logarithmic form, the base of the exponential becomes the base of the log. So the base of this log will be 5, and that's subscripted. And then whatever the exponential equals becomes the argument of the log. And then the exponent is what the logarithm is equal to. So you may hear people say a statement that says a log is an exponent. And I kind of like this statement because in math, the word is understood to be equals, right? So the logarithm is equal to whatever the exponent was in the exponential form. So that little statement may help you as you transition logs to exponentials and vice versa. Again, I had recommended on the previous page the idea of dropping the base and then crisscrossing. So that still works too. I know you'll each kind of find the way that makes the most sense to you. Cool, so that was writing exponential as log. Let's just real quick turn that around. I'm doing this just to be thorough. I know it's fairly straightforward, but we want to give ourselves adequate time to get this important transition down. So now let's take a log statement and write it as an exponential. So I'm asking you to do the reverse of what we just did. So I gave us the statement log base 7 of 49. That's how we could read that. Log base 7 of 49 is equal to 2. And we're just going to revert that back to an exponential form. So I actually think this second example here is a little bit more valuable even than the first, because often what will happen is we'll be given a logarithmic statement, which feels a little bit less familiar, and we'll convert it to exponential, and then we'll feel more like we're at home base. So same thing, the base of the logarithm becomes the base of the exponential, and then we're doing that crisscross with the exponent and the argument. So the fun thing about using actual numbers like I am here is you can check the validity of this statement. Is it true that 7 squared equals 49? Yeah, 7 times 7 is 49. So it's easy to kind of make sure we did that correctly. So that would be a transition from log to exponential. You might be wondering, how are logs useful in daily life? Why should we study them? I think in the exponential section, you probably felt just with even that money application, how exponentials get used. Logs are often used in like speech and hearing science. We use logs to talk about sound and decibels. We use them in chemistry related to pH. They're used for Richter scales, for earthquakes. So there are lots of practical uses for logs also, just to make sure that that's clear too, because a lot of times we don't really feel the need to study something until we know that it does have real life applications. So what else can we do just with this transition between log and exponential? Let's try a little bit of solving. This will be fairly straightforward solving. But let's say that we are asked to solve for x by converting the statement I'm about to write to an exponential form. Just exploring this little connection a little bit more. So let's say we were given a statement log base 25 of x is equal to 1/2. So we're being asked to solve for x by converting it to exponential form. So let's just start by dropping our base and then crisscrossing. So I would get to this statement, 25 to the power of 1/2 equals x. And again, the neat thing is, as we transition from the log form that we were given to the exponential form is very intuitive to us. Now we're just working on solving what is 25 to the power of 1/2, or simplifying, because that is the value of x, right? So x is 25 to the power of 1/2. So probably all I would do to finish this one off is remember that the power of 1/2 is the same as square rooting. That's an important connection there. So when I rewrite 25 to the 1/2 as the square root of 25, it will probably feel a little bit more intuitive there. The square root of 25 is just 5. So that would be the solution to that logarithmic equation. So far, I think we understand that connection between exponential and log form. I'm just going to comment a little bit on the connection to calculators, and then we'll call it quits for this one. So I keep saying that logarithms have bases, right? So we keep writing log base b of x, right, is equal to y, something like that. So b is the base. which I've been saying, but I'm just writing it out now. And it turns out if you grab your calculator, you're going to have two different bases kind of built in as buttons on your calculator. So when you see the log button that most of us are going to have on our scientific calculators, this is understood to be the common log. And if you think about common log, right, we have 10 fingers, that kind of thing. That means it's understood to be a base of 10. So if you ever see a logarithm written without a base, it's understood that it's a base of 10. So log of 7, for example, truly means log base 10 of 7. So it's the only base for which it's understood to be 10 if it's not written. Now there's another button that we're going to have on our calculator, which is ln, and this stands for our natural log. And for those of you who go on to study more like calculus with analytical geometry, calculus for engineers, we deal with natural log a fair amount. And natural log is a base of e. So when we studied exponentials, we started talking about e, such as when we did continuously compounded interest. So if you ever see ln of 7, for example, that's understood to mean log base e of 7. So I wanted to talk about these in relationship to the calculator because you guys are going to see these two buttons there. You're going to see that log button and that ln button. Some of you may have calculators where you're allowed to pick your base too, which is kind of cool, particularly like a Casio scientific calculator, you're able to enter different bases. And if you're on a calculator that doesn't seem to have that immediate capability, we have an easy formula to change our base. So we'll talk about that when the time comes. So I think this should be enough to kind of get you through the introduction to logs. I'll just end with one or two more examples of evaluating a log without a calculator, just to show you how our understanding of the log to exponential definition is pretty powerful. So let's just say evaluate log base 4 of 1 over 64 without a calculator. Okay, so can we evaluate that expression without a calculator? A lot of times what I do is I just start by setting it equal to something so that I can convert it. So let's just say I set it equal to, let's just say equal to y. If I then apply my understanding of the log to exponential form, a correct rewrite of this statement would be 4 to the power of y is equal to 1 over 64. And I'd like to solve this, again, as it says, without a calculator. So I'm going to think about that 1 over 64 on the other side, and if possible, I'd like to be able to express 64 as 4 to a power. So I think about 4 to the first is 4. I think about 4 squared is 16. 4 times 4 times 4, 4 cubed, would actually be 64. So it turns out that 64 in the denominator of this right-hand side is the same as 4 to the power of 3. That starts to look like we can do something. I'm going to take one additional step, which I believe you guys will track with, and that is if I pull the 4 up to the numerator of the fraction, all that it does to the exponent is it makes it negative. All right, so if I move an exponent from bottom to top or vice versa, it just changes the sign of the exponent. So now that I have this statement 4 to the y equals 4 to the negative 3, because the bases match, I believe you'll agree it follows then that the exponents must be equal. So what we did from here to here is we said the bases match. This is a powerful technique of solving related to exponentials. So when the bases match, the exponents must be equal. For a base not equal to 1, right? So our solution here without a calculator is that the statement log base 4 of 1 over 64 will equal to negative 3. Cool. So that's a little bit about logarithms. I think this should be a good intro, and we'll dive into graphing in the next video.